Slope Stability Analysis Methods. Welcome to Blueprint to Reality, the channel where civil engineering concepts are simplified and brought to life. Today, we're exploring one of the most critical aspects of geotechnical engineering, slope stability analysis methods. Whether it's a highway cut, an embankment, or a natural hillside, understanding how and why slopes fail and how to analyze them is essential to prevent disasters. In this video, we'll cover what slope stability means, the common types of slope failure, and the major methods used to analyze slope safety. What is slope stability? Slope stability refers to the resistance of inclined soil or rock surfaces to failure by sliding or collapsing. A stable slope stays in place, while an unstable one is at risk of failing, which can result in landslides, road damage, or even the collapse of structures built above or below. Slope failure occurs when the driving forces, mainly gravity and water pressure, exceed the resisting forces like soil cohesion, friction, and reinforcement. Types of slope failure. Before we look at analysis methods, let's understand failure types. There are three common types. 1. Rotational failure, common in homogeneous clay slopes, where the sliding surface is curved. 2. Translational failure, seen in layered soils, where a planar slip surface forms along a weak layer. 3. Compound or complex failure, combines rotational and translational features, usually in heterogeneous materials. Knowing the type of failure helps in selecting the right analysis method. Why analyze slopes? Slope stability analysis is essential for safety and cost-effectiveness. Engineers need to determine the factor of safety, FOS, which compares resisting forces to driving forces. A FOS greater than 1 means the slope is stable. Common threshold values range from 1.3 to 1.5 for permanent slopes. If FOS is too low, mitigation like retaining walls, soil nails, or drainage systems is required. Accurate analysis helps prevent overdesign and reduces risk. 1. Infinite slope method. Let's begin with the infinite slope method, used for long, shallow slopes where failure is likely to occur parallel to the slope surface. Assumptions. The slope is infinitely long, and soil properties are uniform. It simplifies the FOS equation to a ratio involving cohesion, friction angle, unit weight, and slope angle. Best for sandy slopes, debris slides, or rainfall-induced shallow failures. Limitations. Not suitable for rotational failures or complex geometries. 2. Swedish circle or Finite method. Next is the Swedish circle method, also called the Finite method. This method assumes a circular failure surface and divides the sliding mass into vertical slices. It calculates the FOS by comparing resisting and driving moments for each slice. It's simple, fast, and useful for preliminary analysis. Best for homogeneous soils with potential circular failure. Limitations. Does not consider interslice forces. Less accurate for complex conditions. 3. Bishop's simplified method. An improvement over the Finite method, Bishop's simplified method includes interslice normal forces, but still neglects shear forces. It also uses vertical slices and assumes a circular slip surface. It's more accurate for layered or heterogeneous soils. The method involves iterative calculations, but software tools make this easy today. Best for rotational failures in clay or mixed soils. Limitations. Assumes circular slip surface and vertical slices. 4. Jambo's method. Unlike Bishop's method, Jambo's method allows for non-circular failure surfaces, which makes it ideal for more complex or irregular slope geometries. It also uses slice-based analysis and can be adapted for both simplified and general conditions. The simplified Jambo method is faster but less accurate, while the general Jambo method considers interslice forces for better precision. Best for complex soil stratifications, embankments, and slopes with irregular geometry. Limitations. More computationally intense. Typically requires software. 5. Morgenstern-Price method. The Morgenstern-Price method is one of the most rigorous and widely accepted limit equilibrium methods. It satisfies both force and moment equilibrium and considers both interslice shear and normal forces. It can handle any type of slip surface, circular or non-circular, and works with complex slope geometries and loading conditions. Best for high-risk projects, deep excavations, dams, or where precision is critical. Limitations: complex. Typically requires numerical software like GeoStudio or Slide 2. 6. Finite element method, FEM. Now, let's talk about numerical methods. The finite element method goes beyond traditional limit equilibrium approaches. FEM models soil as a continuum, simulating stress, strain, and displacement in 2D or 3D. It can capture progressive failure, plasticity, and pore water pressure effects. Best for highly complex or sensitive slope problems, large infrastructure projects, or when soil behavior is nonlinear. Limitations: requires advanced geotechnical knowledge and powerful software. 7. Limit analysis method. This method defines upper and lower bounds of the slope's collapse load without detailing the exact failure mechanism. It's especially useful for quick assessments or for validating results from other methods. Best for early-stage design or confirming FOSS range. Limitations: may not provide a precise slip surface or stress distribution. Comparison of methods. Here's a quick comparison. Infinite slope, simple, only for shallow planar slides. Finite, easy but less accurate. Bishop simplified, more accurate for circular slips. Jambu, good for non-circular slips. Morgenstern Price, highly accurate, general purpose. FEM, very detailed, complex analysis. Limit analysis, fast but general. Choose based on the slope type, soil conditions, budget, and available data. Conclusion. In summary, slope stability analysis isn't one size fits all. Engineers must select the method that best suits the site conditions and project requirements. For simple, shallow slopes, go with infinite slope or Finite. For more complex terrain or higher-risk projects, Morgenstern Price or FEM is the way to go. Understanding these methods not only improves safety, but also ensures cost-effective, efficient design. If you found this video helpful, subscribe to Blueprint to Reality for more insights into civil and geotechnical engineering. Until next time, stay grounded and build smart.